Welcome to LMI Collaborative Research and Project Initiative 2020. This initiative focuses on ocean and coastal engineering. The aim of this initiation is to investigate possibilities for executing high-quality research and projects in the area of ocean and coastal engineering that may become a model of activity for other topics. This initiation consists of several activities. The first activities are lectures from the lecturer from the industries, government, as well as the research institute. This will be followed by interview with the policymaker. Then this initiation will be ended with physical or online networking event to seek possibility of collaborative research and project in the area of coastal and ocean engineering. The first cluster, which is in the area of ocean engineering, has been published on the 21st of September. These lectures are from the second cluster, which is the application in the coastal engineering, and particularly in the area of structure and coastal protection. I would like to welcome Professor Brenny van Krusen to give the welcoming remark for this second cluster.
Thank you very much, Ibu Andanawati, for your introduction, and welcome all the people who have found our YouTube channel collab.LMI for this second round of 5 lectures. The lectures today, as Bu Aan said, are concentrated on coastal engineering. And we will see some very interesting research, very relevant to protect the Indonesian coasts, but also to adjust the coast to accommodate the increased activities that require harbors and etc. And all the efforts to keep the environment safe. Safe for flooding, but also environmentally safe from pollution. We thank all the lecturers very, very much for the work that they did to prepare such very interesting lectures. And I give the floor back to Bu Aan to announce the first lecture.
The first lecture for this second cluster is from Dr. Semeidi Husrin. He is from Marine Research Center, Ministry of Marine Affairs and Fisheries of Indonesia. The title of his presentation is Coastal Structures in the North Coast of Java, Past, Present, and Future Challenges. I would like to welcome Dr. Semeidi Husrin.
Hello everyone, welcome to my presentation. First, I would like to thank Dr. Andanawati from LabMath Indonesia for this opportunity on the initiations of collaborative research in the field of ocean and coastal engineering. And now I would like to discuss a topic about coastal structures in the north coast of Java. Before we start, I would like to explain very short about Marine Research Center of the Ministry of Marine Affairs and Fisheries. Of course, you can always visit our website. We, the Marine Research Center, conduct research in the field of marine technology, marine and coastal resources, coastal management, conservation, and coastal hazard mitigation. And our main interest towards the MMF stakeholders. So we focus on the fisheries sectors and also the fishermen related aspect. Our office is in Jakarta, and also we have laboratory in Padang, West Sumatra, in Wakatobi Island in Bali, in Madura Island, Pangandaran, and Morotai. So you can see the distribution of our laboratory and offices almost widely spread across Indonesia. So we also have ongoing international cooperation, for example, with the Japanese of JICA and also with the Joint Research Center of the European Commission, with the CSIRO of Australia, and so on. And regarding our topic discussion, so we would like to propose the research, and because it's our ongoing research in the north coast of Java or Pantura Jawa, because it's economically and culturally very important for Indonesia. It's densely populated, yes, and it's still growing. It's the center of the government, the industry, trade, fisheries, agriculture, transportation, and also we have lots of problems. For example, we have subsidence in the coastal area, we have floods. Here, the local, we call it rob, banjir rob. We also have pollution and shortage of resources, for example, yeah, especially for the fresh water. And we did a lot of mitigation measures in the past, and we will do more because, yes, it's still growing, and we have to do a lot of mitigation measures because the problems are still there. So on the right side, we have example that actually the problem in the north coast of Java started long time ago. So this is the stone inscription found dated back about 4 AD, telling that the king of Purnawarman from Tarumanagara already conducted project of making canals to control floods and also for the irrigation of agriculture area, and it's in Jakarta, yeah, it's near Jakarta, and this inscription itself was found in Desa Tugu or in Cilincing, north coast of Jakarta. So this is just to remind us that the problem in the north coast of Java and also the mitigation efforts started already long time ago until now. And now this is just an example of our ongoing research activities in the north coast of Java, and we did identification on the characteristic of the north coast of Java, and this is one of them. So we conducted identification of coastal erosion and also coastal accretion in the north coast of Java, and this is very important for the basis of the information, because after this we will do more detail, especially on the mitigation measures related to the coastal structures along the coastline of Java. And from here we can get some information. For example, this is very important one here in the central Java. So we have the most severe problems related to the coastal erosion, especially in the city of Brebes and Semarang and Demak, yeah, where coastal erosion is really high in this area. And based on that information, also, of course, we can always get more detailed pictures about the situation. For example, this is some figures for each provinces on the eroded area and on the length of eroded coastline. And we found that once again here the central Java, yeah, it has the most damage of coastline compared to the other provinces in the north coast of Java. And about the mitigation measures, so we already discussed this many times, that we need to do both short terms and long terms. The short terms, we know that it's related to the impact, it's more towards the coastal area. For example, the construction of coastal structures, and for the long term, mitigation measures towards the cause of the problems, finding sustainable solution, including many factors, both structural and non-structural measures. And yes, we also have always ongoing discussion on how to solve the integration upstream, downstream, and upstream of the problems in coastal area, and also know how to get the approaches, the best optimum approaches. Either we use green measures or conventional structural measures. Of course, those need to be implemented also, because we really have to adapt to the condition of the coastal area itself. Sometimes we need one area, for example, green measures can be implemented, but not in other area, because simply those have different coastal characteristics. And this is some pictures of example. Example in June 2nd, 2020, that we had quite alarming conditions, as shown here. This is the case in the city of Pekalongan. So we have seawalls, and in this time, so it's really alerting, because we have high tides, the sea level really rising, and also the waves were really big at that time. So along the north coast of Java, we had big problems. We had floods, or rob, we call it, and then we learned that so we still have so much to do in the future, and how to deal with this flood problem in the north coast of Java. And yes, in our research institute, we have ongoing coastal mitigation research for Pantura Jawa. So it started 4 years ago. So we started with the identification of the existing condition, and then we conducted evaluation, lesson learned, and hopefully in the near that we can develop the optimum model, and also for the implementation directly, because we have now quite firm that the project will be executed until at least until 2024 for the mitigation of flood in the north coast of Java. And yes, quite sure that we have to work together with other ministries and agencies. And these are some of the initial work that we have conducted. This publication can be downloaded from our website. You can go to our website and download this book about the rehabilitation strategy in the north coast of Java. So we started with the big pictures, potential, and challenges of the management. We also talk about the rehabilitation effort, analysis, and challenges. We talk about the erosion and accession in the north coast of Java, mangrove rehabilitation. We also discuss about the effectiveness of coastal protection and policy strategies, and also about the planning of integrated coastal zone management. So this publication followed by the second one. It's more detailed in this second publication. And now for the fourth year also, we started to go deeper on the assessment of coastal structures in the north coast of Java. The reason why we conducted this, because we learned that coastal structures in the north coast of Java not only belong to the Ministry of Public Works, but also belongs to, for example, MMIF, ours, also belong to the Ministry of transport, belongs to the local government, belongs to the private, belong also to the Ministry of State-owned companies, for example. So we have so many coastal structures. For example, this one, so it's about breakwaters in the north coast of Java. So we also have, for example, we identified about port and coastal reclamation. We learned from here that actually in the past we have quite a lot of reclamation projects in coastal area occurring in the Banten province and also in the East Java province. And we have distribution of fisheries port also and port on each provinces in the north coast of Java. So this information I think is very important when we are trying to find a solution in the future in order to get the more sustainable coastal mitigation measures. Seawalls in the north coast of Java, we also identified this, and yes, it's quite in line with the identification previously about erosion and accuracy in the north coast of Java. Here also the same. So we found that Central Java and East Java province, they have most seawalls constructed compared to other provinces in Pantura Jawa. And also for the groins, the same. Yeah, it's mostly used for the mitigation effort of coastal erosion. So we have more groin structures in Central Java and East Java, but zero in Jakarta. And also we have jetty access channel structures along the north coast of Java. It's quite a lot in West Java and Central Java because we have so many fisheries port inland, entering the rivers. And to make sure the safety of the boat, the fisheries boat entering and going out the river mouth, so they constructed jetty access channel, and the numbers are quite a lot. Of course, by having all this kind of structures, then it will influence the dynamic of the coastline in the surrounding area. Also for the ports with jetty structures, it's also quite a lot. And the north coast of Java, this is quite makes sense because north coast of Java generally are shallows. So in order to reach require depth for the port, then they have to construct jetties quite long offshore in order to get the harbor deep enough so big ships can berth in the port. So in this case, we have more structures in Banten province and also once again in Central Java province. And not only identification using satellite images, so we also this year visited some interesting places in the north coast of Java. These are some examples. So we found quite interesting results of both conventional and nature-based mitigation measures for coastal erosion. And on the left side, we have pictures from the city of Cirebon, for example. Rocks could be very, very good in protecting mangrove, and tambak belongs to the fishermen there. And for the case of the city of Semarang, for example, the use of structures, hybrid engineering, it's quite successful. As we can see that sedimentation is quite growing quite fast over there, and yeah, mangroves also grow very well. There is another case also, for example, in the case the city of Demak here, the local government, they constructed concrete structures made of buis beton. So here in Indonesia we call it buis beton, this cylindrical concrete filled with sands and concrete Here we call it beton. And yes, after some time, this structure is quite successful in trapping sediment and growing some mangroves. And we learned also that when we visited this place, these structures already extended to this side. Yeah? So they have more concrete now at the moment. And also we visited the city of Pekalongan and Semara Island in Brebes, and we learned that the use of geotextile, I think it's quite successful, yeah, in trapping sediment, for example. So yeah, it's quite surprised actually. It's more than 8 years already, for example, for the case in Pekalongan, and more than 4 years for the case in Brebes. Here in Pekalongan also we learn the importance of coordination. For example, this is the city would like to have flood protection along the canals. Unfortunately, they have many fisheries boats, and MMF would like to construct the new fisheries port onshore. Unfortunately, this cannot be done. Yeah, the progress was were very slow, and they already started just to construct the breakwater, but not other important infrastructure. So all the fisheries boats remain along the canals, and the problems on how to start the construction for the flood protection becomes problems, because the Ministry of Public Works cannot immediately start the construction because there are so many fisheries boats parked along the canal. And this is also another example, the need of new ports and port infrastructures. This is the case in the city of Tegal, for example. As you can see, that there are so many coastal structures protecting the port belong to the Ministry of Marine Affairs and Ministry of Transportation. I was just thinking that how to get some to get the effectiveness and the efficiency of the coastal structures, for example, by removing some structure here and making just 1 or 2 breakwaters in order to save more money and to get more spaces also for both ports, yeah, belongs to the fisheries and to the Ministry of Transportation. And this is very important also about the presidential decree number 79 2019. So this is can be the basis, yeah, if you would like to have a proposal, yeah, or a research collaboration in the future. This is about economic development in Central Java, and also about priority for coastal flood mitigation measures as requested by Mr. Jokowi, our president, that will be focused on Jakarta, Cirebon, Pekalongan, Semarang, and Demak. And there is also a commitment that the government would like to spend, to allocate, yeah, around 54.9 trillion until 2024. So the conclusion, so development in the north coast of Java will continue, and we have the basis already. And increasing problem in coastal area will be there. We have floods, pollution, shortage of resources, more investment therefore still needed, especially for the environment. Cooperation and coordination remain a challenging task in the future. So we need to learn from the existing measures, especially the existing coastal structures, because those are the source of knowledge. And for the research opportunities, we need, after we learn from the existing structures, so we need to find the best sustainable coastal structures, integration, short and long-term solution, nature-based, conventional, and so on. So thank you very much. We welcome research collaboration. You are welcome to visit us anytime, yeah, in Ancol, North Jakarta. It's quite a nice place. And if there is opportunity, so I would like also to have more discussion with you. Please contact me anytime. Yeah, so I put my email address here. Thank you very much.
The next lecture is from the Ministry of Public Works and Housing, Directorate General of Water Resources. Protection of the coast is extremely important to prevent sedimentation. Sedimentation loss at the beaches, for instance. It's not only protecting, it's even, as we can see in this lecture, reconstructing original, much larger sandy beaches by using geotubes. It's a very inventive way to recover and extend the sandy beaches. I'm very happy to announce the presentation by Professor Dr. Dede Sulaiman. Please go ahead.
Good morning, selamat pagi. Thank you for the opportunity to deliver a presentation about my activities and current research and development and future research plans. This presentation divided into two parts. First, related to my last activity in developing low-crested breakwater or PEGAR. The last one related to the next research and development, especially in use of in situ mud sediment as a pillar of geotextile tube. My name is Dede Sulaiman. I am a principal researcher in the field of coastal engineering. Formerly, I worked at experimental station for coastal engineering or Balai Pantai at research center for water research in Buleleng, Bali. After reorganization of the Ministry of Public Work and Housing, since August this year, I was placed at the Experimental Station for Hydraulic and Geotechnic or Balai Hidrolika and Geotechnik Airan at Directorate of Water Resource Engineering Development or Bina Teknik Sumber Daya Air in Bandung. My expertise in coastal engineering is mainly related to dealing with coastal erosion problem. One of the innovation in the coastal pocket structure is the development of a low-crested breakwater structure or pemecah gelombang abang rendah. Let me give a show about PEGAR and the product that have been produced related to the development of this type of breakwater. PEGAR or low-crested breakwater is a coastal protection structure which placed parallel to the coast with the crest level of the structure is located between the mean sea level and the high water level. This is here. The crest level is minimum at MSL or between MSL and high water level. The concept and function of low-crested breakwater or PEGAR. The concept is with overtopping and with breaking, promoting sedimentation behind the structure. And function of PEGAR or LCB, the first is with energy dissipation, decreasing transmitted wave behind LCB structure, causing lower energy as reaching the coast. As current rotator, generating circular current that promoting sedimentation process behind the structure and lessening or reduction of longshore drift, causing the longshore drift accumulated on the beach. And then as a sediment trap, sediment transported through wave overtopping and longshore drift accumulated behind the structure. And the last one is structure that encourage and support the formation of salient and tombolo behind the structure. This is a prototype of PEGAR or geotube, The field experiment conducted on 3 different types of coast. First is sandy beach at slip slope, Second, at sloping sandy beach and at muddy coast. This is a current pattern around Pagar. As the name implies, Pagar is a coastal production structure that is always overtopping with waves. The armor on Pagar is still under attack, causing the waves to break. The difference between Pagar and conventional breakwater lies in the diffraction of waves, which are more dominant in Pagar. Likewise, the reflection of wave toward the sea is more dominant in conventional breakwater. Another difference is that amount of wave energy that can overtop over the structure. Conventional breakwater retain most of the wave energy. On the other hand, Pagar pass some of the Pagar energy over it to the shadow area behind the structure. This is the function of LCB Pagar, reduce and prevent and control beach erosion, and then form new shoreline. The innovation of conventional breakwater structure is carried out through dimensional modification, namely by cutting the crest elevation of the structure, which is then directly proportional to the reduction in volume and cost. Another innovation is by applying the use of geotextile tube filled with sand to increase the added value, namely reducing dependence on natural stone, which is becoming scarce. This is a geotube, Pagar geotube filled with sand. The development of Pagar is based on a series of experimental results in the laboratory and in the field, resulting in a structure that has protective effectiveness with relatively cheaper construction costs than conventional breakwater. Research and development of Pagar began in 2009 through a physical model test at experimental station of coastal engineering at Ciparai and at Bandung Regency. The main function of this Pagar structure is not reduced with energy breaking, with becoming from the deep sea either in a perpendicular direction or at angle to the beach. When passing through the Pagar structure, will break and produce a rotating current behind the structure. The current behind the structure generated by the breaking of this wave rotates in direction, weakening each other and encouraging the formation sediment deposit in the coast. This current circulation phenomenon causes the formation of salient and tombolo, which makes the beach wider as well as restoring previously eroded beach. This is the first field experiment of Pagar with geotube at Anyer Beach, Serang, Banten. This is condition of the coast before geotube installation on 22nd of December 2010, and then after 6 months of the installation, we conduct a monitoring, shoreline monitoring at 8 June 2011. That is a shoreline ching from steep to sloping beach. This is Pagar geotube at Tanjung Kait at 2011, and this is the first application of Pagar geotube by government, especially from major city of Pekalongan, beginning at 2012 until 2014. This is the condition of beach after the construction of geotube at Sari Beach, Pekalongan Beach. This is a condition that look about wider beach and inviting tourism, local tourism to the beach. This is geotube at Sigandu Beach. This is Sigandu Beach, Batang, November 2014, 1 month after the construction, and we conduct a monitoring 2 years after that at May 2016. The right side look very wide beach. This is also about Sigandu Beach before and after the construction of the geotube. This is also the same. And this is a monitoring ratio of Sigandu Beach, Batang, 2015 and 2016. Okay. This is about pegar geobek bambu prim at Sriwulan, at Madikos of Sriwulan. This is 2 years after that we all conduct in collaboration with PKPT, Pusat Kajian dan Penerapan Teknologi, and Breeding with Nature. We install 200 meter of pegar geobek with bambu prim at Timbul Soko, Demak, 2017. Also here, we have a fact that the new shoreline invites local tourism. For example, for Bali Beach in 2019 and Bantang Beach here in 2015. Tombolo formation behind LCB of Pelabuhan Beach. This is a condition, beach shoreline condition 3 months after geotube installation, and the right side Tombolo formation after 6 months of geotube installation. This is the condition of pegar geotube at Pelabuhan Beach, Bali, 2018. And the last one, this is the intention of pegar SCB geotube at Suksia Beach, Batal, 2019. We use 3 kinds of geotextile tube. The first one is non-woven geotextile tube. The second one is composite, and the right side is woven geotextile tube. Relating with the product of pegar development, we have 63 papers related to coastal protection and low-crest breakwater or pegar. And also we have 3 certified patents and 7 registered patents, and 10 books published, already published. This is 10 books published about pegar or LCB and beach erosion. The more actual, we involved in international seminar on coastal engineering. The most actual is ICC 2020 at Sydney and become virtual ICCE 2020. We have a paper about the role of geotextile tube as low-crest breakwater in restoring shepherd beach erosion on Bali Island. The next one is overview present research agenda and suggest possible collaboration, especially about development of geotextile tube filled with in-situ mud sediment. Pegar geotube filled with sand has been carried out in all prototype questions such as Pasir Putih, Anyer, Tanjung Kait, and so on. Meanwhile, the pegar percussion on a muddy beach was carried out by the construction of a 200-meter-long pegar geobek bambu frame in 2017 on Timbul Soko Beach, Sambodho Beach, Denmark. This is the product of field experiment of pagar geobag installation with bamboo frame at Sambodho. There is 200 in length for segment with a gap of 5 meters. And this is in relation with the next research and development in using geotextile tube filled with Insitu mud sediment. From the experience in installing pagar geobag on a muddy coast with sand filling, it is obtained that the implementation time is longer because the filler sand is imported from outside the location. Therefore, to increase the effectiveness of installing pagar or LCB geotube on a muddy coast, the use of in-situ mud sediment will be developed as a filler material for geotube. This development not only for the purpose of filling pagar or LCB, but also can be applied for other purposes such as the core layer or sea dike and repeatment. However, before arriving at the decision to choose the filler material, a proven study and analysis is needed both in the laboratory and in the field. This is scheme of sludge sediment filling to geotube. This is a slurry farm and then polymer dissolver. This is a polymer dissolver. This depends on the kind of the mud solution. The polymer inject into the geotube and then become coagulate. The slurry pump or dredger pump the dredging slurry into the geotube. In line, the polymer solution is directly injected so that the mud particle bind and to each other into block clumps. Inside the geotube pocket, the solid mud block is retained while clear effluent water flow out of the pores of the surface of the geotube. This is a scheme of development of mud sediment as a filler for geotube. We also discussion with Tenket Indonesia and we talk about the feasibility of using mud sediment to become a filler for geotextile tube. They have technology and it itself is feasible to conduct in Indonesia. Here it can be applied on land and coastal water. Filler material in the form of sand for hydraulic marine expansion or shale clay sediment as beneficial reuse of water dredging material. Geotube application can reduce the need for rock in the construction of coastal protection building. For example, core of coastal embankment, core of sea dike, or fresh water or perimeter embankment in reclamation project. It can be stacked to achieve the effective design target height. This is simple, cost-effective, environmentally friendly, and the best alternative for embankment structure in coastal water with soft clay sediment. This is a concept design to install geotextile tube filled with mud sediment. Here is a 3 level. First level is 3 geotube. Second layer to geotube, and at crash level one dede. This is a construction design, can be used as a core layer of sea dike. This is case study yaitu application at Saka Energy West Pangkah Energy Project. This example here. This is a pagar or LCBQ to fill with mud sediment on muddy coast. Prepare with cerucuk and bamboo rafting to protect settlement. Therefore, we invite an upper cooperation in the development of mud sediment to fill geotextile too. The result of this development are not only for pagar needs, but also can be applied for other core layers, such as sea dike and other coastal structure. That is what I can say. I hope this is useful, and I'm looking forward to cooperate in the next research agenda. Thank you. Terima kasih.
The next lecture is from Insitu Teknologi Surabaya, the Department of Offshore Engineering. It is about the impact assessment in the Madura Strait, which give entrance to the Surabaya harbor. Clearly, because of sedimentation, dredging has been done regularly to keep the possibilities that deeper ships enter the Surabaya harbor. But besides that, also new activities are developed along the Madura Strait. In this lecture, you see the impact assessments for that development. I'm glad to introduce Dr. Kriyo Sambodho for this lecture. Please go ahead.
Hello, ladies and gentlemen. My name is Kriyo Sambodho. I'm very honored to be here with you all to share some of my experience related with the development and research in a coastal area. Also, I want to thank to Bu Andonowati who invited me as one speaker for her program. Hopefully, we can have a fruitful discussion through this presentation. Okay, without further ado, I will share my slide. Hopefully everybody here can see the slide clearly and also can hear my voice clearly. The topic of today's discussion is about impact assessment due to development of heavily crowded coastal area with the special case of Madura Strait in East Java province. And my name is Kriyo Sambodho. I'm a lecturer in Offshore Engineering Department, Faculty of Marine Technology, ITS, Surabaya. We move to next slide. Actually, this slide tells us about the timeline of the coastal area development. Our topic of discussion today in last 36 years. We can clearly see the development of this coastal region from 1984 to 2020. Here we can see between 1984 to 1995, there was only one jetty built owned by this company in Gresik, but entering 2005, there are another one jetty built. Entering the 2020, this coastal area has become very crowded, marked by a lot of jetty built here. So maybe you can guess why there are a lot of jetty here, because there are a lot of factory here that need this jetty for berthing the ship for production, export, import activity. Now, let's move to next slide. I took this slide from ICTS application. Maybe you have already familiar with the application, this application, ITS application, because last meeting Professor Ketut Buddha, I think, described a lot of things related with this application. I took one figure from the ICE ETS, especially in the region of Gresik, in focus of Madura Strait. You can see clearly here that there are 3 offshore pipelines entering Gresik region and have a onshore receiving facility in Gresik. And the next, you can see how crowded this area, because you can see here clearly there are marks of a lot of ships waiting for entering the main port in Surabaya. Also, you can notice here, as previously I mentioned, a lot of jetty built here. It means there are a lot of factories along the Madura Strait in Gresik region. That one become a main problem that I will discuss with you all today. Let's move to next slide. Let's focus to this area I marked by circle. This is the development is a very rapid for accommodating increasing production capacity. So it is clear that increasing the production capacity, they need ship to transfer their product to another location. The problem is the access to the regional or main port is very, very limited. It means there is only one small road connecting this region to the regional port, small port in Gresik area, or also it is too far if they want to go to the Surabaya city. So that's why several factories here want to construct its own, we call small port. But that development will raise another problem. For example, of course, due to very crowded access in the Madura Strait, one of the problems will be safety of the access channel. I will omit this discussion. I will only focus the discussion today for point number 2, number 3, number 4, and number 5. That problem actually come from the dredging and reclamation activity. Let's talk in more detail. Because we discussed about the problem, let me to give you a background related with the environmental condition. This slide shows the result of current velocity measurement and tidal fluctuation measurement. Here we measure the presentation in Bahasa, but I can explain to you. Actually, we have been conducted 2 days of measurement from 3 different vertical positions. That one is 0.2 D. D is water depth, 0.6 D, and 0.8 D. 0.8 D is mean close to the sea bottom. The conclusion of this measurement we can see in this figure. During high tide, the current velocity varies from 0.02 to 0.6, but during low tide, the current velocity is around 0.03 to 0.9 with this direction like this. How about the tidal fluctuation? After we process the data, we found that the high water level is around 1.35 and the low water level is around minus 1.37. So it's almost same, I think, the fluctuation between high tide and the low tide. I mean, the amplitude is around this value. Let's discuss about the ground condition. This bore log is obtained in the 2 different locations in the area of study. We can see here in the surface up to 5 meters mostly consists of clay sand. But started from 5 meters, consists of medium silt clay. These two area is a very soft, very soft, because we can notice here the SPTN value, so the very small number. But below the level of minus 12 meter, we can find very stiff clay with an SPT varies from 30 to 60. And grain size with the mean grain size, grain diameter is varies from 0.003 in the offshore region and 0.04 in the nearshore region. What we can conclude from the grain size diameter? Okay, let me remind you related with the Houston diagram. I think all of you have already familiar with Houston diagram. Houston diagram is like a rule of thumb for assessing the sediment transport problem. If we plot the main diameter of in this area, in the area of study, and together with the velocity, current velocity in that region, we can come to this representation, the sediment area. What this mean? This means that sediment particle in the area of interest is continuously transported due to very small particle. That one is the clay size mainly, and the current is relatively fast, from 2 centimeters per second to 90 centimeters per second. So it's mean related with Houston diagram, we can imagine that sediment in that area will continuously transported or continuously moving. So we can guess that in that area will need dredging in order to facilitate the ship for berthing, because the ship need at least 15 to 20, at least 7 to 15 meters depth to accommodate the ship. So I give you the illustration here. What's happened if we dredge the seabed soil? The possible impact is seabed instability, release particulate matter, reduce light penetration, or release the toxic chemical, because the coastal area here mainly is used for factory activity. So a lot of toxic will be thrown to the sea. The one problem is related with the soil stability due to dredging. As I previously mentioned, most of the port near the region at least will accommodate the ship will draft around 6 meters. So that's why the existing seabed condition will be deepened by dredging, so will approach to the 6 meter depth. So the area can accommodate the ship with the draft of a 6 meter. The problem is how stable the soil bed after the dredging, and also how about the slope? Appropriate slope, soil slope, underwater slope in this region, so the soil can keep stable. We use two kinds of approach, analytical method and numerical method, for assessing the problem. And this is the result. Both of analytical problem and finite element approach for this problem come to the solution that with the slope of 1 to 6, the stability is very good. It's marked by safety factor around 1. But if we increasing the slope, become 1 to 5, the stability is not good. So it's been the soil slope will collapse. The slope body soil mesh here will collapse if we construct the dredging with 1 to 5 slope. So this indicates the result of effect of soil stability due to dredging. Also, we conduct soil stability due to reclamation work. As we can illustrate it here, this is the design figure, and the figure in the above is our sketch related with the related with the design. So we can see here, this is the reclaim area, the green area is the reclaim area. And then in the end of the reclaim area, there is a quarry stone placed in the end of the area in the ocean area. So the reclamation land is designed, can withstand with a design load of 30 kilonewton per meter square. So this illustrates the design of the reclamation area. We conduct, again, numerical experimentation using analytical method or finite element method, and we investigate how stable the construction, the reclamation design is. So we come to the result that with the analytical method, without loading, so the safety factor is around 1.5. It means it's okay for the construction, and the with loading of with surface loading of 30 kilonewton per meter, the safety factor is also around 1.5. But slightly different results showed by the finite element method. Safety factor when we simulate without loading, this one is around 1.3. But I think we can consider it as good design. And also with loading, the safety factor came with a value of 1.3. So in this case, we can conclude that the design of reclamation area is can be fine. The next, we can consider that, you know, in the beginning of my presentation, I saw that there are at least 3 pipelines entering that region, entering that coastal area, and the pipeline is buried because the development of the area that needs reclamation. So that's why this figure in the left hand, in my left hand, is illustrated the situation while the buried steel pipeline in the reclaimed area. And the reclaimed area will be used for maybe, for example, for crane, forklift, and etc., and so on and so forth. So we will modeling using the finite element model. This is the geometric model, and this is, we come to the solution of the finite element method for the buried pipeline, come with this solution. Another problem is related with environmental assessment due to dredging activity. We can see that the mainly material in the region is a clay. So the clay will be transported in the form of suspended sediment. Our government standards say that a maximum allowable value of the waters in that area should be meeting this criteria. For water quality example, for TSS should be around 80 milligram per liter. This means we located in this area, so a bit we can see a bit clearer than the other in my right hand side. So we should investigate, we should assess whether when the TSS become normal as a government standard after dredging activity. This environmental assessment due to possible sediment transport condition after the reclamation. The figure in our left-hand side is illustrate the before reclamation condition, and in right-hand side is after reclamation condition. And this gray area is illustrate the reclamation part. Here we can not see the reclamation part because this illustrates the before reclamation project. As we can see here, actually the sediment deposition is here very high inside the port area. After the reclamation, however, after the reclamation, we notice that there are small part of sediment concentrated in this area just in front of the newly constructed port. This means that regular maintenance dredging will be needed in this area. Now we move to next slide. in this case, in this problem, we predict that the sedimentation, the sediment will be settling down after 20 days after the reclamation project. So the government, our government need this estimation about the when all of the sediment settling down by using numerical analysis, as previously mentioned. We can predict that maybe about the 20 days, all sediment will be settling down with the final sediment concentration profile shown as in this figure on our right-hand side. We use this kind of a method to assess the vertical distribution of sediment concentration. We can see here after 20 days of reclamation project. So 20 days after the reclamation project, the sediment concentration is likely significantly below the government allowable value. That one is 80 milligram per liter. All methods shown that the value will below the maximum government regulation. Now, so we come to the our recommendation to that factory that will do a dredging activity at the time. We recommend to use silt protection sheet to prohibit the sediment enter the clean water area in the open ocean. So that's why we also design the suitable silt protection sheet to keep the sediment with the high concentration only in this area. This is just example of the application of the silt protection sheet. Next problem is related with the shifting of that position. Because of reclamation project, of course, the outlet position is shifted further to the ocean region. So that's why the ocean, actually the previous location is around here. So now around here, though, is shifted in front a bit in the close to the ocean area, far from the shoreline. I mean, we model two kinds of transport, that one ammonia and nitrate, and I will discuss with these two slides, this slide and the next another slide. This is the result of the model of transport and dispersion of the ammonia. As we can see here, the model during the MSL, water level in the MSL position, water level in the LLBL position, and the water level during HHWL position. So we can notice here the ammonia is dispersed like this in the MSL, but in a low level, during the low water level, the value is lowest than if we compare with the during high water level. Next is about the transport and dispersion of nitrate. Almost similar with the previous ammonia simulation. We can model the simulation of transport and dispersion of nitrate during in the time of a water level in MSL position, water level at the position of low water level, and water level in the position at a high water level. So that's all in my presentation. By this presentation, I hopefully we can raise a discussion with related hot issue in the coastal area development, as we can notice together that in my presentation, a lot of problems arise due to a port development. I believe in the near future, another jetty will also construct in the port area of in the coastal area of a Gresik region along the Madura Strait. So I think that one is invite our collaboration together we can solve the problem there by using our experience in numerical modeling. Hopefully, my presentation can increase and deepen our understanding about the problem in the coastal area in Gresik region, where the industrial sector there is a very active in that area. Thank you very much and see you in the next occasion. Thank you.
The next lecture is from the Port Infrastructures and Coastal Dynamic Technology Center in Yogyakarta, part of BPPT. You will see their capabilities and facilities, modeling with various software, beautiful laboratory with many experiments, and the combination with environmental data, all for harbor and coastal structures and protections. And we see many examples about that, and it gives a possibility for future activities and future collaborations. I'm glad to give the floor to Ibu Dr. Khusnul Wardani.
Hello everyone, I'm Khusnul Wardani from the Laboratory for Harbor Infrastructure and Coastal Dynamic Technology BPPT. Today I got an assignment from Dr. Wijo Kongko, who the head office of my laboratory, to deliver a lecture at this event. First of all, we would like to thank you for giving us the opportunity to join this event. Hopefully we can create research collaboration after this event. Today, I would like to deliver a presentation with the title, Recent Technology in Modeling for the Solution of Port and Coastal Dynamic Problems. This is the contents of the presentation. The first is about BPPT and our laboratory at a glance, and then the second is about some of experiences, and then the third is ongoing research project in 2020, and then the last is the potential topics for research collaboration. So let me start the presentation. Our laboratory is located in Yogyakarta and our main office is located in Jakarta. In the previous event, Dr. Erwandi from Petrin BPPT has already explained about the BPPT organization and a little bit about our laboratory. I would like to show you a brief about our history. The Laboratory for Harbor Infrastructure and Coastal Dynamic Technology BPPT, we call it PTIDP, was established in 1982. This laboratory aims to study the stages of building a breakwater of Port Pulau Bayi, Bengkulu. After the project had been done, the laboratory donated to BPPT and now transformed into the Laboratory for Harbor Infrastructure and Coastal Dynamic Technology BPPT. The next slide is about organization in our institution. We are under coordinating of Center of Technology for Maritime Industrial Engineering or PETRIM. And then this is our position in this organization. The main task of our laboratory is to carry out infrastructure and coastal dynamics technology services. We conduct a survey of hydrooceanography, topography, and soil investigation. And then we do numerical modeling, also physical modeling, and port and coastal structures design as well. This is the main facilities of the laboratory, such as numerical modeling. We have MIC 21, SMS, and etc. And then physical modeling, we have wave basin and waveforms. In port and coastal structure designs, we have Flow 3D, SAP 2000, and Praxis. In the right side is about human resources. that content of doctoral, master, and bachelor. So the next slide is about our competency. Start from defining the research scope and then continue with field survey and then modeling, including numerical modeling and or physical modeling, and then finally design and recommendation. In here, our scope is in hydrodynamics, wave penetration, structural stability, coastal processes, coastal morphology, oil spills, and pollutant dispersion, and tsunami as well. So this is our facilities in physical modeling. These facilities had been recently revitalized with the current technology in 2019. We have a wave basin and two wave plums with a specification as mentioned here. So this is for wave basin. Include irregular and multi-directional wave. And then this is the second facilities is wave plums. And then the third is with phlegm as well, with concrete as well as in the wall. So this is facilities in numerical modeling with some modules in its software. We use Mic 21, and then we use coastal engineering design analysis and surface water modeling system as well. And then we develop a tsunami software. We call it Tsunina. This is certification for laboratory accreditation. The left side is for inspection body under ISO 17020, and then the right side is certification for laboratory for testing and ISO 17025. The next chapter is about experiences in our field. We conducted a jetty inspection for ex-Antam port at area 70 in Cilacap. We conducted in 2019. This is the process of inspection and structural modeling of the jetty. In this project, we conducted a concrete test, steel test, corrosion potential test, and finally structural modeling using SAP 2000. This is an experience in physical modeling. We conducted physical modeling in 2D model to study the performance of coastal protection stability in Balongan, belongs to Pertamina. In this research, started with defining modeling test scenario, and then continue with basic research test, and then running model and analysis of the result. So this is our facility in physical modeling that used in this project. So this is other experiences using 2D and 3D physical modeling. And then this is the project experience in the last 10 years that consisting of inspection, survey, field survey, numerical modeling, and invention. So in 2010, we had an invention about the artificial armor layer. We call it BPPT lock. And then this armor layer had been deployed in PLTU Pacitan, East Java. This is our activity when the disaster occurred. We modeled the parameter that we got from UMKG and USGS, and then we plot the result into a map. The result is our initial assumption for disaster event before we conducted a post-tsunami survey. So we joined the national and international team to conduct a post-tsunami survey in Indonesia. We recorded all evidence to verify our tsunami model for predicting the impact of the next disaster. This is the physical modeling for the tsunami. So in here, the aim of this model is to know the performance of mangrove on tsunami reduction. And then the below picture is about the Krakatau model we conducted in wave basin in 2011. The next slide will talk about the ongoing research project in 2020. This is a brief title of our research. So we have RDS or Read Down Station modeling for supporting innovation system and technology of Indonesia tsunami early warning system. And then the second is clearing technology of SIDAC for National Capital Integrated Coastal Development Program. And then the third is study on the seaplane dock development. And then the fourth is building resilience earthquake and tsunami in East Indonesia. Collaborate with BPPT, LIPI, Brunel University. And then the last is field survey and inspection in some location in Indonesia. The first is about the RTS modeling for supporting the innovation system and technology of Indonesia tsunami early warning system. This is a flagship in BPPT. We collaborate with BMKG, BIG, and BG, and other units in BPPT. So in here, this is the structure of Tsunami Monitoring Center for Indian Ocean region. And in here is Indonesia part. And in here, the National Tsunami Early Warning Center structure with Indonesia, BPPT in here developed tsunami buoys. And this is BPPT-IDP's contribution from 2020 to 2024. The first is operational tsunami monitoring and analysis system for DSS Indonesia Tsunami Early Warning System, and then the second is tsunami prediction system with near real-time modeling and integrated for Indonesia. The third is nearshore hydro-oceanographic and onshore topographic data to support INA CBD. And then the last is tsunami mitigation construction design standard. This is some result of this research. The left side is about tsunami modeling in South Java. In here is graph about tsunami height, and then this is about the tsunami arrival time. And then the right side is tsunami modeling in Rokatenda, and this is the time arrival of tsunami in its observation point. The second is about SIDAC clearing technology for the National Capital Integrated Coastal Development Program, or NCICD. This is a national program. We collaborate with Bappenas Ministry of Public Works and other units in BPPT. The aim of this project is to assess the performance of the SIDAC with earthfill dam type, caisson type, and backfill system with container reinforcement type. So So the research scope, like mentioned in here, the first is about field survey data processing and mapping. And then the second is assessment of hydrodynamic coastal processes and water quality. And then the last is assessment of alternative design of sea dike structures. This is the result of this research, although this is on still existing condition. So the left side is thermal distribution in Jakarta Bay in existing condition, and then the right side is the simulation model of structure for sea dike with earthfill dam type. And then the third is about study on the seaplane dock development. This is one of the national research priority. We collaborate with LAPAN, BPPT, PTDI, ITB, Ministry of Transportation. The aim of the project is to provide the infrastructure design for the flight test of N219 amphibious craft. So our laboratory contribute to seaplane dock development in here. The last chapter about the potential topic for research collaboration. So we divided into two groups. The first group is about post infrastructure, and then the second group is about coastal dynamics. In the port infrastructure, we can create a research collaboration in navigation channel problem, floating breakwater, and then sediment problem in port area, including dredging technology, and then port inspection, port development, seaplane-based development, and etc. And then the right side, we can create research collaboration in coastal dynamics, in tsunami and coastal hazard research, coastal processes, coastal zone management, coastal protection in small island, eco-coastal protection, and etc. So that's all of my presentation. Thank you very much. We are looking forward to collaborating research with you.
The last lecture for the second cluster is about HAWASSI. HAWASSI is a software developed at Laboratorium Matematika Indonesia. This software has been developed over more than 10 years. In the first cluster, we presented HAWASSI for the application of ocean engineering. In this second cluster, Dr. Ruddy Kurnia and Dr. Arnida Latifah will present HAWASSI application on the coastal application.
Hello everyone, I'm Ruddy Kurnia. Together with my colleague Arnida Latifah from LabMath Indonesia, we would like to present HAWASSI simulation for coastal engineering application. I will present the first part of this presentation about wave on coast interact with structure as in harbor, and the second part of this presentation regarding bathymetry reconstruction from X-band radar images will be presented by Arnida. This is an overview of HAWASSI. HAWASSI wave module. The governing equation of HAWASSI wave is based on Hamiltonian Business formulation with Dirichlet approximation. Nonlinear wave, breaking wave, varying bathymetry, and bottom friction can be modeled with fast computation. HAWASSI can simulate wave in coastal area with very complex interaction with bathymetry and harbor structure. In HAWASSI, we can also simulate or design extreme wave as in deepwater Grabner Sea. Wave radar module. In this module, we will look to the wave that mostly known as a circulator from X-band radar images. The radar can be placed at the coast, at the harbor, or on the ship. In the module, we try to reconstruct the wave radar images based on dynamic averaging and evolution scenario and produce spatial temporal wave data. Prediction of incoming wave to a blind spot area, for example, in the ship position, can be done for 2 minutes. The wave prediction can increase walkability in offshore activities. From the radar images, we could also reconstruct bottom profile that will be explained in the second part of this presentation. Wave ship module. This module is based on Hamiltonian business fully coupled wave ship interaction. In the module, we can deal with linear or nonlinear waves, ship-free motion or moor motion, ship sailing, ship-ship or ship structure interaction. For example, this is simulation of near-shore moor ship. The simulation has been shown in the first lecture of collab.LMI in Ocean Engineering section. In the next slides, we will show simulation related to coast and harbor. This is an overview of near-coast processes. Wave propagating from deep ocean to shallow coast show large changes in the wave profile, wave speed, wavelength, wave height, and direction. Wave reach shallower water near coast, especially in shoaling zone, let's say depth less than 20 meters, wave speed decreases, wavelength decreases, and wave amplitude increases. In surf zone, steep waves start to break, then downside of average waterline, followed by run-up on the beach, wet and drying. This process can be seen quantitatively in the experiment and in the simulation as shown in this figure. This is a plot of average temporal phase, mean water level, average temporal trough. Quantitatively, the average crest amplitude shows shoaling process, breaking process, and run-up on a shore, while downside can be seen in the plot of mean waterline. HAWASSI wave software has been validated with experiment data extensively. For example, harmonic wave propagate above submerged bar based on Beji and Bajes experiment 93. In this simulation, we can see wave soaring in upslope, wave getting steeper and break at the top of the bar, and then decompose to smaller wave at downslope. The up-down blue points are measurement wave elevation data. The lower plot shows statistic comparison of maximum temporal crest, mean water level, minimal temporal trough, significant wave height, skewness, and asymmetry. The simulation results are in agreement with measurement data. Spilling wave breaking above a slope, Kirby 94. In this test case, we validate our result not only wave elevation, but also kinematics, horizontal and vertical interior velocity. Breaking bore simulation. For non-breaking case, our results are similar as WAY95 using fully nonlinear potential flow curve. Wave soaring Birkhoff 82. In the simulation, we observe wave soaring refracted due to underwater harm. Lower plot show bottom profile and comparison with measurement data. This is harbor wave simulation. Wave entering harbor with access channel. This water depth at the influxing zone and at the access channel are 21 meters. At the left side and at the right side of the channel are 11 meters. A wide, long, and deep access channel is required for large ships to enter or exit the harbor. Abrupt change in the topography can cause the wave energy concentrates or attenuates at the entrance to the harbor depending on the direction of the incoming wave. The input for the simulation are the significant wave height 4.7 meter, the peak period 14.5 seconds, directional spreading 20 degrees. The performance of HAWASSI are compared with other software, for example, Mach21, SWASH, SWAN, in terms of bias, which is average error of significant wave height of 10 buoy measurement, and absolute deviation error with respect to the bias. Based on that, HAWASSI has best performance. Short-crested wave penetration into harbor. This is another harbor simulation that located at Limassol, Cyprus. The animation show wave entering the harbor. The wave disturbance density plot show mostly high wave disturbance are at the front of the harbor. Comparison with the measurement data of normalized significant wave height show the simulation result reproduce the experiment data very well. This is harbor simulation in which the experiment conducted by Delta RES. This is photograph of experiment design showing harbor layout. This is our simulation result, harmonic wave entering the harbor, density plot of significant wave height, and comparison with the experiment data at buoy position. The HAWASSI simulation could help in designing optimized experiment and to reconstruct the experiment. Our HAWASSI software is able to simulate ship sailing in canal or river. With the ship sailing simulation, we could obtain safe ship routes and speed limit, study effect of ship-generated wave to a canal bank or structure, and using wave radar, we could provide a real-time traffic control. This is a validation case with TU Delft experiment. Ship entering a canal, and in the canal there is a port entrance. There are 4 wave measurements inside the port. This is a comparison of wave elevation at buoy number 2. This measurement denoted by a blue line plot, HAWASSI VBM by red plot, and Delft Pass software result from TU Delft by green line. The ship position in time is shown by the straight dark green line. It can be seen from this plot the ship-generated wave arrived at buoy number 2 much faster than the ship, and when the ship arrived at the port entrance, the wave in deep trough profile. After we validate our software, we try to do study case of Cikarang Bekasi Laut inland waterway. Government is constructing CBL canal with aim to reduce car traffic load in highway from the Tanjung Priok to industrial area Cikarang Bekasi. The canal is 25 km long, with width 55 width and 4.5 depth as shown in this cross section. This is the terminal layout, and in the corner there is the turning basin for the ship. We did simulation to obtain ship speed limit and acceleration for CBL such that the ship-generated wave do not disturb activity in the terminal. In our simulation result, the speed limit is 8 knots, acceleration 0.2 meter per second square, and the limiting wave height 50 centimeter. Now I'm going to talk tsunami on Jakarta Giant Seawall. This is an infrastructural plan to reduce risk of flooding in Jakarta and to include a large sea dike for retention area. Part of the plan dike has the shape of iconic Garuda. LabMath Indonesia, together with Pusair, Ministry of Infrastructure, did a numerical simulation to study effect of possible Anak Krakatau tsunami at the planned Garuda dike in Jakarta Bay. These are our research questions from the study. If Anak Krakatau in Sunda Strait explode as in 1883 explosion and create tsunami, what is the expected wave height in Jakarta Bay and at the giant seawall? Can the future wall withstand the tsunami wave? Not only the simulation with the proposed Garuda wall, but we also do simulation with our optimized wall. The wall has a shape of the part of the circle with optimizing the wall length, total area, and total wet area. These are both simulation results for Krakatau explosion 1883 at the left and Anak Krakatau at the right. For initial condition for Anak Krakatau simulation, we take a quarter energy of Krakatau 1883 explosion. The wave arrived at Jakarta Bay approximately 2 hours after the explosion. At Jakarta Bay, we thought the wall, significant wave height up to 6 meters for Krakatau simulation and up to 2 meters for Anak Krakatau simulation. Now we'll look simulation with proposed wall and optimized wall in the detail for Anak Krakatau tsunami. In the simulation with the proposed wall, there is wave energy concentration at the head of the Garuda wall. Crest height up to 10 meters, the trough -5 meters, and significant wave height 10 meters. For the optimized wall, the wave smoothly guided, no wave concentration, leads to much lower significant wave height, mostly 4 meters, that is comparable to height of the common strong wind wave. This slide finishes the first part of the presentation regarding HAWASSI wave simulation in coastal area or harbor. Next, the second part regarding HAWASSI radar module for depth construction will be presented by Arnida Latifah.
Hello everyone, my name is Arnida Latifah. Here now my presentation about HAWASSI radar module for depth construction. The idea is that the impression of sea can give us a feeling how deep the sea is. Therefore, the software is developed to answer how the pattern profile of the sea looks like by only seeing the sea surface wave. As we know, pitch changes over the time can be caused by erosion or sea level rise. As an illustration, a beach over the slope of 1 in 100, like in Cilacap, 1 meter depth change will bring to 100 meter pitch difference. One of the coastal erosion that takes scientists and government more attention is the coastal area at Northeast Bali. Based on the observation, the shoreline changed up to 200 meters during 73 years. It means that the shortening beach may reach up to 2.5 meters per year. So, HAWASSI radar image software can help to determine the depth. It is very useful for monitoring erosion process cheaply, controlling mitigation action like sand supply or breakwater, and of course for protection of Indonesian territory. So, from the X-band radar, electromagnetic waves sent to water surface are partly reflected back to radar, except when blocked by higher wave in between, so-called shadowed wave, but this can be backscattered to produce a shadowed images every rotation time. Then, from the radar images, we do a reconstruction of the shape to get shadowed image that will be used as an input of our HAWASSI radar software. By the principle that wave speed reduces in shallower water, wavelength decrease and period constant, then from the observed period, the depth follows. Our HAWASSI radar software then can estimate the depth of the sea. For an example, we present a synthetic data of wave simulation which is shown in this figure. The simulation is done by this actual pattern profile. Using these images, the HAWASSI radar software compute the depth and it results a good estimation as shown in this figure. For the real case, we have an experiment in Cilacap done by BPI, Bahari Berjaya Indonesia, that is funded by RISPRO LPDP. The experiment aims to test the hardware and software in the wave dynamics and in the reconstruction of the depth. The experiment consists of sea surface observation using X-band radar from one point at coast, located approximately here, and there were also a bathymetry and wave spectrum measurement that will be used for verification. From the measurement, we get a wave spectrum and shows that the measured sea depth is a combination of swell wave with period of 8 seconds and also the local wind wave with period of 5 seconds. From the measured radar images, we try to reconstruct the wave by converting to wave elevation and filling the shadow zone that is shown by the blue area in the plot. Once the wave is reconstructed, we can use the images to estimate the depth by observing the wavelength variation from the images. Not only using one set of images, we also use other set of images that are measured from other time frames with different observation period. Here, we use between 7 seconds to 12 seconds images with shorter wave. Give much better estimate at shallower part, where images with longer wave can predict at much deeper part. Therefore, we estimate the depth for each set of images and average all of the results to get the better estimated depth as shown in the lower plot here. If I may summarize about HAWASSI, it is a Hamiltonian structure of the dynamic equation for potential flow simulation and ship dynamics. It's up to third order nonlinearity, can implement variant bottom from the deep ocean to the beach, breaking process, also bottom section. It uses pseudo-spectral implementation with result of fast simulation. For the ship module, we can do all possibilities of the wave simulation, more or free-sailing ships and ship interaction. For the radar module, it can transfer radar images of sea state into detailed wave elevation. It simulates wave faster than physical time to get prediction of future wave on the ship. At near coast, it can do a depth reconstruction. So that's all about HAWASSI. Thank you very much.
This brings us to the end of this cluster of 5 lectures on coastal engineering. We thank all the lecturers very, very much for the effort they did to give such beautiful presentations. The topics are really very interesting, and it's clear that there is still a lot to do in the future. In the coming times, as Ibu Aan in the beginning already explained, LabMath Indonesia will conduct several interviews with stakeholders. These interviews will be put online, after which we aim to have a physical/online meeting with many people present. That will be in the beginning of December. Please contact this YouTube channel for the announcement near the end of November. We thank you very much all for having participated in this activity that was partly also subsidized by the Foundation of Scientific Research from the Netherlands, NWO. Thank you very much for your interest. Hope to see you at the next activity. Thank you very much. Good day. We are now entering our institute, LabMath Indonesia, where most of the work on our software is being done. And I would like to introduce the people who are at this moment involved in all the research. The first one is Nunu. Nunu, I would like you to introduce yourself by giving information about your past education and etc.
Yeah, hello, I'm Nunu. I'm just finished from the master degree from Utrecht University, and mainly I am working here, and then also partly I am a research assistant at ITB, at Department of Mathematics, and here I'm helping with the software to extract the wave feature from the radar images and then convert it into depth reconstruction.
Okay, what are your future plans, Nunu?
I'm planning to get another degree with a PhD degree in the oceanography.
Okay, thank you very much. Then on the same bench is Ruddy Kurnia. Ruddy, please introduce yourself.
Yeah, I'm Ruddy Kurnia. I'm starting working at LabMath Indonesia since 2011, and yeah, after I finished my master from Japan and ITB, and then I did internship at LabMath Indonesia. From LabMath Indonesia, I get the PhD position at the University of Twente, and I finished for 4 years. And after I finished my PhD at Twente, I back to LabMath Indonesia working on the postdoctoral project almost since 2016, and now I'm mostly working on the web simulation, developing HAWASSI with the team, and web sheet modeling.
Okay, thank you, Ruddy. The next one on the other bench is Latifah. That is one of the people who work in a collaboration with LIPI. LabMath Indonesia has collaboration and staff exchange with LIPI. So Nida works most of the time now on topics from LabMath Indonesia. Please, Nida.
Yes, I'm Arnida Latifah. I'm working at Indonesian Institute of Sciences. Now, in collaboration with LabMath, I'm also working in LabMath in developing HAWASSI software. I'm mainly focused on developing the coupling between our software HAWASSI into CFD.
Thank you, Nida. Then besides Nida is Dura. Dura works here for a little bit less than a year now. Dura, please introduce yourself.
Hello, so I'm Dura. I've just started working in LabMath Indonesia from the start of this year. So I was graduated from Delft University of Technology. My work here is mainly doing the simulation of ocean wave using our software. And then currently I'm still in the process of applying for position for a lecturer position in ITS.
The topic that you did for your previous work and the work here, Dura, is very different?
It's different, but the principles are the same because I was actually studying in geophysics. We usually not dealing with ocean wave, but seismic wave. So even though that they are different, that they are still waves, so I still can catch up to do the work here.
Okay, thank you. Waves, waves, waves. This is Ayu, also in the collaboration with LIPI. Ayu, please go.
My name is Ayu Sabrina. So I work at a research center of informatics, LIPI. So I just joined this LabMath Indonesia in this year at March. With the collaboration with LIPI and LabMath, I had the opportunity to join LabMath Indonesia through the internship program. And then I do mostly do the simulation of waves using HAWASSI simulation, HAWASSI software.
What is your aim in the coming years, Ayu?
Yeah, I have planned to continue my study to do PhD.
Okay.
In mathematics.
In mathematics.
Yes.
Thank you. These are the people at this moment employed at LabMath Indonesia. And you heard the topics, and they are part of, mainly we are working on our research agenda that is developing software that is useful for Indonesia, that has a lot of water around it, but also gets interest from people abroad because our LabMath work leads to very good software HAWASSI that has been presented in two presentations, because everything is part of two main topics on our research agenda. One is to work for the future ships. Future ships will be autonomous, not anymore steered by people, but completely autonomous from information from outside. And of course, ships should become zero emission in 2050. That requires a lot of work. And the other topic is also with waves, but then near the coast, namely the coastal protection and infrastructure. Those are the most important topics that all the people here work on. So that gives an idea of both the people. I must say that sometimes in the past years we had many more people, also students doing PhDs and master theses. So if they are interested, they can always write to info@labmathindonesia.org so that we can see if our interests match and whether they can have here a good place to study and to write their thesis.